Hello to this short video. Here I want to just very briefly explain to you the connection of this kind of band diagram we have been looking at, where we look at E over the direction X, to this kind of band diagram you might have seen in some other lecture. So this here is a band diagram of silicon, and this is also called not the band diagram, but typically the band structure, if you have this kind of diagram. And actually, if you look at the differences of the two, first of all, you see that both have the energy E on the y-axis, but this diagram here has the wave vector k on the x-axis, while this diagram has the spatial direction x on the x-axis. So in this diagram here we have just the spatial direction, we have the conduction band, the valence band, and the band gap Eg. And if we now want to see, well, where are these values in our band structure as it is shown here, then we have to look at which band, so these bands here are the loud states, which band is the band with the highest filled state at zero temperature, and that is called the valence band. So here the valence band is actually this parabola shape. And which is the lowest band that is not occupied at zero temperature, which is the conduction band, and it is this band shown here. So we can find the valence band and the conduction band by looking at which states in the band structure are occupied or not occupied. I mean, you don't see it just from the diagram, but you have to have more background knowledge of which of these states now is the state that is occupied at zero temperature and which is not occupied. Okay, that means we can find these energy values here. And then the relation between the two diagrams is such that you can imagine this diagram here. It is just plotting the lowest energy value here that is unoccupied, and that is the conduction band H. And it plots also the highest value that is occupied here, and that is the valence band H. So in this diagram, you only see the band edges. You don't see the whole band structure as in this diagram here. And therefore, it is a simplified presentation that for each space, if it's a uniform semiconductor, so we just have one piece of silicon, for example, then independent of which position we are at, we will have everywhere the same conduction band edge, so the same energy, that state that is just not filled at temperature equals zero, and we will have the same valence band edge, which is the state that is filled. And then, of course, the electron-hole excitation, if we absorb photons, it means that we will have a transition from this lower state to this upper state. And as one side remarks, you can already see here that the highest filled state and the lowest unfilled state are not at the same wave vector. And this means that silicon is an indirect semiconductor. A direct semiconductor would be that these are at the same wave vector on top of each other. Considering now that the wave vector can be kind of seen like an impulse, and you need to have impulse and energy conservation, or momentum and energy conservation upon interactions, it means that here actually the interaction between this state and this state is called indirect, in that sense that it's not at the same momentum just going directly up. But more on this later. Thanks for watching.